Hey everybody, this is kind of the last of the basics of equilibrium, and I'm doing something a little different. You can see that I have decided that I'm going to put my mug right down here. That way I can look at you. There you are. But regardless, let's talk a little bit about Le Chatelier's principle and how changing concentrations or changing the reaction will affect the equilibrium position. Okay, and so Le Chatelier's principle right here, again, if you want to copy that down, the idea is that as we change the system, or as we put a stress on the system, the chemistry will make sure that the system will shift in order to reduce that change. Kind of like real life, right? We have a lot of stress in our life. We kind of shift what we're doing to reduce that stress. So there's a lot of different changes that can happen here. So let's talk about change in concentration. If we increase the concentration, okay, we have reactants are in equilibrium with products, okay? And so you can write all of these down if you want. It's not a big deal if you do or not, but let's take, what if we add reactants? Well, we now have increased the amount of reactants, so the system, the equilibrium reaction, is going to want to get rid of those extra reactants. So what's going to happen is, to maintain equilibrium, this reaction is going to shift to the right, okay? Or, if you prefer a mathematical approach, what we can do is you can talk about how the equilibrium constant is products over reactants, okay? That equals K. And so if we increase reactants, in order for this to go back to equilibrium, the amount of reactants is going to go down a little bit, and the amount of products is going to go up a little bit, so that that ratio is back to the equilibrium values. And so if we increase the amount of reactants, we shift to the right. And you can imagine that, I'll do this in a different color here, if we increase the amount of products, now we want to shift to the left because we want to get rid of the products for exactly the same reasons. If you can understand that concept, then Le Chatelier's principle is, I guess, fairly straightforward. Okay, and so what if we have, and I don't know if this is actually going to move my picture, but I can move it up here. Okay, what if we, now instead of adding products or reactants, what if we take them away? Well, I would hope that you would see that it's kind of the same thing. Again, reactants are in equilibrium with products, and so now if we take these away, the products are going to shift to fill that vacancy that was left by taking away reactants. And then the opposite is also true if we take away products. Okay, and so what if we change the pressure of a gas reaction? Let me see if I can throw this. I don't know if this is actually doing anything, so you may be looking at like, what are you talking about, Walsh? Anyways, what if we change the pressure? Well, remember, pressure is proportional to concentration, and so we should treat that just like if we were changing concentration. Okay, and so we're talking about gases, and if we increase the pressure of nitrogen, it's going to shift away from nitrogen and things like that. Okay, now here's an idea of what happens with Le Chatelier's principle. Okay, this is the Haber process, and so remember the Haber process is N2 plus 3H2 is in equilibrium with NH3, and this is two of those. Okay, and you can see that this is 1, 3, 2, okay, so it's kind of symbolized here. And so what happens is we are at equilibrium. At this point, okay, we can tell because the concentrations aren't changing, or the partial. So we can tell because the partial pressures aren't changing here, not the concentrations. Anyways, sorry for the little hiccup there. But at this point right here, at this time, what we do is we add H2. So we're increasing the amount of H2. So that's an excess stress. So the reaction is going to shift away from H2. So by doing that, we increase the amount of NH3, and we decrease the amount of N2, because in order to form the products, we have to use up even more N2 than we originally had. Now notice when we do this, when we reestablish equilibrium, the new amount of H2 is going to be greater than the original equilibrium amount of H2. We added H2 to the reaction, and so that's what ends up happening. Okay, so you can see this kind of graphically. Okay, now here's a legit, let me put this up here, I guess. Here's a legit engineering example about this, and this is how they make ammonia in real life. Okay, so N2 plus 3H2 is in equilibrium with 2NH3. Okay, and so here's where it all starts right here. N2 and H2 are introduced. The reaction goes on here, it's heated up, and then what happens is that they remove NH3 from the system. Any sort of unreacted starting materials gets put back in here and ends up going back at the beginning. But what happens by removing the starting materials? When we remove those starting materials, now there is a deficit stress, and the reaction will shift toward the products. So what we're doing is we're forcing the reaction to make more products. The equilibrium is going to continue to shift towards the NH3, towards the products there. And so this is kind of a real-life example of how Le Chatelier's principle is used. Now, here's the kind of funny thing. When you think about change in volume of a system, now you're not talking about changes in pressure really, but you can kind of consider it as a change in pressure. But I'm going to kind of skip over this a little bit, and this is from the book. But if the system gets, if the volume is decreased, okay, so you go from, let's say we have a balloon. Okay, now you get to see my real art ability here. Let's say you have a balloon, and that balloon then shrinks, okay? You put it under a lot of pressure. So now the balloon is getting smaller. So now that takes up a lot less space. So what's going to happen is, because it's taking up less space, there's less, you want to shift to the side that has less moles of gas so that those moles of gas will take up less space. Because what you're now doing is because when you make it smaller, you're changing the concentration, changing the pressure, so you need to go back to the equilibrium pressure that was there. And the only way to do that is by having the reaction shift toward the side that has less moles of gas. Okay? And then, of course, the opposite is true. If now you increase this, the other example, other than a balloon, is a piston. Okay, a piston is a closed system, and so if you have a piston and that piston changes its volume, now what you're going to do is you're going to increase the volume. So now, because you're increasing the volume, you have more space for the gas, and you want to go back and maintain the equilibrium pressure, the equilibrium concentrations of the gases. And in order to do that, you have to shift to the side that has more moles of gas. And so by shifting to the side with more moles of gas, you can maintain the equilibrium. Okay, so if we think about the Haber process, okay, again, the Haber process, N2 plus 3H2, and all of these are gases, okay, NH3, okay, what if you decrease 2NH3, what if you decrease the equilibrium? So you take a balloon and you make the balloon smaller, or you have it in a piston here, and then you push down on the piston, so now your volume is smaller. Which way is that going to shift? Well, you have less space, so you have less room for the moles of gas. So you are going to shift to the side with less moles of gas, and so by changing the volume, you're going to shift to the right. Okay? Now, this is like drum roll. Okay? The only thing that affects the equilibrium constant is temperature. And I've been talking about this since we started equilibrium. Okay? And so if the only thing that affects the equilibrium constant is temperature, we should probably figure out how that works. Okay? In order to do this, we have to delve in just very quickly into thermodynamics. We will go further into thermodynamics later. But what we have to do is we have to talk about the heat in a reaction. Okay? There are two types of reactions when we're talking about thermodynamics. Those that release heat, like combustion, and those that need heat, like when you have an ice pack, a chemical ice pack that you get when you're playing sports or something. Okay? Now, when you have these, you can treat heat as a reactant or a product as such. So let's say you have an ice pack. Okay? An ice pack needs heat in order for the reaction to continue. What it does is it takes heat from the outside, from the surroundings, and it converts that heat into chemical energy to cause the reaction to go forward. The result is we end up using the heat and turn it into something else. So there is a lack of heat. The heat goes inside and is converted. So what happens is it gets cold. Okay, and I'll put that up here. Cold. Okay, that is called an endothermic reaction. The heat goes in and is converted, so it gets cold. Now, just the opposite would be something like a combustion reaction, and I will appropriately change this to red. Okay, like a combustion reaction, now you have the heat that is being released. There's extra heat, so because there's extra heat, this is going to be a hot reaction. And now, because heat is being released, heat is considered a product. That being said, now we can treat heat, or temperature, which is the measure of the quantity of heat in something, we can treat the heat as a reactant or a product, and then apply Le Chatelier's principle to it. Okay? So, if you have an and this is an endothermic reaction. If you have an endothermic reaction, what happens if you increase, let's make sure that I just, let's see, the reaction is heated. If you increase the heat, Le Chatelier's principle says that you're going to shift the reaction towards the products. But notice by doing that, the equilibrium constant is reactants over products. By doing that, you're making products and changing the reactants, and so, but you're not increasing a reactant, an actual reactant. Oop, I miswrote that. This is, erase that. I don't ever want you to ever think that it's reactants over products. So, products over reactants. Okay? When we're not adding any reactants to it, so this only decreases and the amount of products increases, and that serves to increase the equilibrium constant mathematically. And so by heating a reaction that is endothermic, you'll get more products. And that stands to reason. Think logically or chemically about it. It's endothermic, it is seeking heat, and so by providing it more heat, you're going to get more products out of the reaction. Okay, and so what if we have an exothermic reaction? Okay, and now if this reaction is heated, okay, now this works backwards. Again, we're gonna shift to the left, and K equals products over reactants, and because we haven't added any products, the amount of products of all of the products decreases, the amount of reactants increases because we've added heat, and therefore the equilibrium constant gets smaller. And again, I think that makes sense chemically, because what is an exothermic reaction? It is a reaction that is producing heat. It's got excess heat to give up. So if you provide more heat to the reaction, it's going to not produce as much. It's already producing heat. So you give it more heat, then it's not going to want to make any more products. It's going to want to stay as reactants. Okay, so I think that Le Chatelier's principle makes sense, but temperature is the only thing that affects K, because you're not actually adding reactants or products or taking away reactants and products physically to shift the reaction. You're only changing the heat, and so that's what happens. Okay, so here's the question. Again, you can pause this and try to answer it on your own, or you can wait. So, and you can let me work through it. Okay, so methanol is produced one way, this way. So this is methanol. I wouldn't expect you to know that that was methanol, except that you probably know that that's carbon monoxide and that's hydrogen. Okay, so the only thing that's not the thing that you know is methanol. Okay, but now we want to know, should we do this at high or low temperatures? Well, it's an exothermic process. So exothermic process means that the heat is here. And I am going to symbolize heat as delta H. Okay, that's the thermodynamic symbol for heat. Well, it's actually the thermodynamic symbol for enthalpy, but nonetheless, that's what I'm going to use. Okay, so now, if I want to commercially produce methanol, there's an assumption that I'm making. That means that I want to produce as much of this as possible. So now the thought process is that if I want to produce as much of this as possible, I want to have the reaction shift to the right. The only way that I can have the reaction, well, there's two ways that I can have the reaction shift to the right. Okay, I can increase the amount of reactants that are there, but that's what I'm going to do anyways. Okay, if I'm commercially producing this, I'm going to increase the amount of reactants. But how can I play with the temperature to get this done? Well, what I can do is I can create a deficit stress, or I can cool this down. And by cooling it down, I'm now taking away the heat that it is producing. And by doing so, this reaction is going to shift to the right and produce more methanol than it would at higher temperatures. So in this case, the reaction should be done at higher or at lower temperatures to get a higher yield of methanol. Okay, so we'll work through some practice problems, and there it is. That's Le Chatelier's principle. Every equilibrium chemist's favorite Frenchman. Okay, have a great day.